Now we did as far like deal with the section dealing with chirality as far as stereochemistry. I'm gonna go to the section of stereochemistry. I'm gonna deal with a thing called chirality. Chirality, what chirality does, chirality refers to handiness. As far as your hands, you got a left hand and a right hand. You can take your left hand, you can basically put like a mirror between your left hand. The mirror of your left hand would be your right hand. The mirror of your right hand would be your left hand. You also got the same thing with your feet. You got the mirror of your left foot would be your right foot. Left foot, right foot, something like a little cat in the head type one. But now if you take, for example, take your hands, you actually want to put them on top of each other, you see that your hands have thumbs on two different opposite sides. Also take an effect when you actually try to put different gloves on them. You just got like a left glove and a right glove, you just put one glove on randomly. You can tell when you got the wrong glove and stuff on because your thumbs would not fit right. You also, for example, if you do like taking a screw and actually try to screw it into wood, the screw actually goes only in one direction. When you screw in one direction, it goes down. Other direction, it comes out. It doesn't go in both directions, but it goes both in and out in both directions. For those who are left-handed, you also realize that there are different type scissors. For people that are basically right-handed, you don't really realize that there are two types of scissors. But if you're left-handed, you realize there are two types of scissors. Also, probably in elementary school, you also realize as far as desks, there's a handiness to the desk when you sit on the desk. Because you're a left-handed person, you got an awkward way as far as like sitting in a school desk as far as trying to write. Most desks are actually designed for right-handed individuals. And most of the population actually will be right-handed. There's actually a percentage of left-handed individuals too. Now I will say back in the day, if you were growing up years ago, if you were you start using that left hand, you get that left hand popped. Don't be using that left hand. Go back to the right hand. Like they stopped doing it for like more. They kind of like not trying to focus that, but when you're growing up earlier, for older individuals, you use that left hand as far as like writing something like that. That left hand got popped. You need to go to right hand. Now, as far as the organic molecules, we're going to have, again, because like the organic molecules have little teeny tiny hands. We're going to have another way as far as giving the handiness organic molecules. Chirality is seen in organic molecules that have carbon atoms with 4 different groups attached. In this molecule, we have 2 carbon atoms. In our 2 carbon atoms, let me draw my bonds. We have carbon 1 and carbon 2. How many different groups are attached to carbon 1? How many different groups attached to carbon 1? 3. How many bonds are carbon 1 to form? 4. So I see I have 4 numbers. So we got an H, an I, a Br, and what's the 4th thing attached to carbon atom? A carbon. Are any of those 4 groups the same?
Yes. Well, not. No.
Because remember, here's my group. Put my atoms up there. I got a Br. I got an I got an H, and I have a C. Those are my 4 groups attached to carbon atom. any one of those 4 groups the same? No. That's a carbon with 4 different groups. If I look at carbon 2, do I have 4 different groups in that molecule?
Not deep.
Here's my 4 groups. I got a hydrogen, a hydrogen, a hydrogen, and a carbon. Are those 4 different groups? You cannot have 4 different groups if 2 of your groups are the same. Carbon atoms with 4 groups are called carbon atoms. Carbon atoms with 4 different groups attached are called carbon atoms. So carbon atoms are carbons with 4 different groups attached.
So entirely it's seen in carbon atoms.
Yes, the lihanin is seen in carbon atoms. Now we get the lihanin as far as carbon atoms. Again, I'm not going to end. I'm just going to have to end up showing this for like a little background as far as little particular values. When we got as far as testing the molecule, integration, we got a Br, we got a C, an H, and an I. We're going to do a group as far as to try to determine if the molecule is going to be a left hand or right hand. Again, since carbon atoms in general do not have, or molecules in general don't have hands, we can use a letter representation to indicate left hand or right hand. To assign this particular, to assign our 4 groups, we're going to actually look at a periodic table, and we're going to assign the molecules according to atomic number. We have bromine, carbon, hydrogen, iodine. Which of the molecules has the highest atomic number? Iodine. The atom with the highest atomic number was given a priority rule of 1. Highest atomic number, then going down. This is group 1. The second highest atomic number. Bromine is given 2. The third highest atomic number. Carbon, which is given value of 3. And the last, the one with the least atomic number, will be hydrogen, we're given value of 4. So I'm going to put a 1, 2, 3, 4. Actually, the more I get into a particular part of it, without trying to set the background and stuff up, we're only going to really be able to do is one definition, which is chirality. So basically, for like stereoisomers, we can take that off the exam, and we can also take off the exam enantiomers, diastereomers, and meso. Because again, I don't want to really throw that. I don't want to kind of throw the definition out without at least giving like a background leading up to it. And also the number of possible stereoisomers. Also not going to work for us. Because I do want to at least kind of give you the background about how they set the stuff here up. But as far as how to set it up, only thing we do it now for exam number 2 would just be the definition of carbon atoms. How to determine chirality of carbon atoms. Number one, relax. Number two, identify the chiral carbon atom. Great. Assign the four groups attached to the chiral carbon atom. Just assign the four groups attached to the chiral carbon atom. Arrange the groups in order of atomic mass. Give the value of 1, 2, the group with to the atom. Most time atomic number, atomic mass will kind of go hand in hand with each other. I have to use atomic mass because, again, the reason I use atomic mass, because, for example, you can get a tower with carbon atoms. Carbon also have isotopes of different carbon. Carbon with an isotope with a molecular mass of 13 will have a higher priority than a carbon with a mass of 12. Carbon with a mass of 14, because it's 3 isotopes of carbon, carbon 12, carbon 13, carbon 14. But again, for most of the rules and stuff, you probably get away with just using atomic number. But you can also get an atom in which you have like more than one carbon atom, in which the carbon atom itself actually kind of have a higher priority than one of the other ones, based upon the atomic mass. But for most of the time, you can always get away with atomic mass or atomic number. Atomic number really will be fine for like 95% of the time. There's like a little small percentage of the time which, if you do atomic mass all the way through, you're fine that way. If you do the atomic number, you're fine 95% of the time. In most of the cases, atomic mass, atomic number will go basically pretty close hand in hand. Give the value of 1 to the atom, or to the group, to the group. With the highest atomic mass. Number 2 to the second highest. Number 3 to the third. Etc. Number 5. Take a curved line and connect number 1 to number 2 to number 3. 6. If the curved line is clockwise, use the letter R. If the curved line is counterclockwise. Use the letter S. Seven. This is a relative configuration. Or the absolute configuration. Group number 4 determines the absolute configuration. If group number 4 is 4, configuration is opposite. If group 4 is back, the configuration stays. The configuration stays. Or stays. And you use those rules to determine the RS configuration of any carbon atom. So what I want to do is kind of relax. First we identified our carbon atom. In this case, the carbon atom is carbon number 1. The next thing we did was to label the 4 groups attached to carbon number 1. When I did my 4 groups, I started with the top and I kind of went clockwise. So I started with the top, Br, followed by C, followed by H, followed by I. Going from the top, just going clockwise. What I try to do is get a routine, and I'm becoming OCD with my routine. Once I got my groups, I would then find my atoms on the periodic table, and I'm arranging them according to atomic number. High atomic number, atomic mass. For atomic mass or atomic number, iodine will be 1, bromine will be 2, carbon will be 3, hydrogen will be 4. So I put on my molecule the numbers 1, 2, 3, and 4, which will give me my groups from number 4. Next, I'm going to take a curved line, and I'm going to connect the numbers 1 to 2 to 3. Taking a curved line, connect the numbers 1 to 2 to 3. Let's go all the way around. When I connect the numbers 1 to 2 to 3, am I going clockwise or counterclockwise?
Clockwise.
Remember, for the right where the clock goes is right. This video we're going clockwise. Going clockwise, I will get the letter R. But remember, we counted to 4 numbers. How many numbers have we used so far? 3. Remember, don't count the number 4, because number 4 get the final say-so. For number 4, you gotta find group number 4. Is group number 4 forward or backwards? And you're probably saying, how do I know it's group number 4 forward or backwards? Because it's not shown either forward or backwards. Like, I don't know which one it is. To do this, when you have to go to art class. I'm gonna do my little art drawing. In order to pass the class, you must be able to draw at least this way. And you're probably saying, hold up, what in the world that little picture got to do with anything? We're going to have little pictures right here to kind of represent the little group of stuff here we're going to. We got a head, we got our feet, and on the side here will be our arms. If I take my arms, what does either do my arms to make them to draw, to put my arms forward or backwards? Forward. Just like your arms, everything to the side is understood to be forward. It's understood to be forward because no groups for here is actually the side of being forward or backwards. When you do forward or backward, we do what we call like a dotted line and a wedge type arrangement. And here, there's no dotted line or wedge arrangement. Since there's nothing associated with being forward or backwards, we will go to the default arrangement, which is your picture, your self-portrait. These represent your arms forward. Either do your arms being forward. For your head and your feet, so it's kind of warm outside. When you go to a beach party and you want to do the limbo, how low do you go? If I were doing limbo, where's my head and my feet? If I'm doing limbo, head and feet will be back. In this case, BR represents my head and H represents my feet. I'm looking at group 4. Is group 4 understood to be forward or backwards? Backwards. Since 4 is back, the configuration stands or stays. The absolute configuration of the molecule here would be R. Yes.
You said the feet is.
If you do the limbo. If you do the limbo, even you go ahead and practice yourself when you do the limbo. When you do the limbo, you're going to have your feet out in front of you. So you're going to be able to balance yourself, have your feet in front of you. Remember, you got your feet in back when you do the limbo, going backwards, right?
You must not be good at limbo.
I mean, I can't see. I mean, I want to see you pull off with your feet forward and you leaning back like this here, but your feet is forward. You have to have your feet back or behind your body in order to have a balance. So that's when you go back, you have to get your head back. You have your head back here, trying to get up to the road. But again, if all you do is kind of do your little drawing here, kind of represents your head and your feet. Head and your feet understood to be back. Arms, just like I do the arm stuff here. Now you put your arms backwards, but like you get a little real cringe in your back as if we start pulling backwards. But as far as arms naturally would go forward as compared to being backwards. So just like your arms on your body, this understood to be forward. These two groups understood to be back. Go and do maybe another mark. Yes.
Will it always line up like that though? Like, would it always be 1, 2, 3, 4?
No, it's not always good. It doesn't have to line up. We will give you one in which it don't line up. And what I'm gonna do, I'm gonna take the same molecule, I'm actually going to take 3 and 4, kind of move them right. Might end up getting rid of my middle part here. So I got a molecule, I got H, I got a BR, I have an H, I have a CH3, and I have an I. This is how I got my little groups and stuff. I didn't label them, just try to change my little label here. This is 1, That will be number 2. This is 3, and that's 4. Now, I didn't mention as far as here, since you break it up. When you're doing a little 1, 2, and 3, you have to go in the order 1, 2, and 3. You can ignore number 4 in your connection between 1, 2, and 3. So when I do my little connect from 1 to 2 to 3, 1 to 2 to 3. In my 1, 2, 3 connection, I don't have to worry about 4. 4 comes up in the very last step anyway. Now you cannot go from 1 to 3 to 2. You still got to go in order of 1 to 2 to 3. So we're connecting them, going from 1 to 2 to 3. What direction am I going in connecting 1 to 2 to 3? Clockwise, which is R. R would be my relative configuration. Next, I'm going to turn my absolute configuration. In my absolute configuration, I need to look at group number 4. In my stick figure, where's group number 4? At my head and my feet or my arms? Your arms. What's your arms understood to be? Forward or backwards? Forward. So the group number 4 is understood to be forward. My configuration will be opposite. What's the opposite of R? S. The molecule would be S.
It'll be S
Because the final say-so comes from group number 4. So remember, like I mentioned earlier, we had you have a relative configuration, but your absolute configuration determined by group number 4. Since group number 4 is forward, it gets the opposite. Now, as far as Edward asked me as far as the little solid line and wedge lines. You can take this what's called like a molecule with not either forward or backward, and you have to take the molecule and convert it to a 3-dimensional molecule. Remember in our arrangement, we said that everything for the head and feet was understood to be back, arms understood to be forward. So we take a C, H, I, BR, CH3. You're going to use a solid wedge represents forward. We have a dotted line represents backwards.
Is that? I thought it was like a dotted wedge, and then wherever the wedge opens up, it's going to be, or wherever it's smaller, it's going to be towards the central carbon, and then where it opens up, it's going to be in the back rather than the front.
Now, don't try to trick you that much about those. Now, some of you get like a different kind of shape type thing. Some people, solid wedge, always end up giving you being forward. Dotted line always end up giving you being backwards. They're not going to try to do a whole bunch of trying to trick you about far like the different shade between a dotted solid wedge and a solid wedge one. They're not going to do that particular part for you. So if I want to do this molecule, I will have the bond between carbon and Br will be shown as a dotted. Carbon and C will be dotted. And the bond between carbon and I will be a solid wedge. And the bond between carbon and hydrogen will be a solid wedge. Now, how would you rate this molecule as far as doing a 3-dimensional structure? For a 3-dimensional structure, I'm going to take 3 of my atoms and I'm going to keep it in the board. And I'm going to show the other 2 atoms being outside the board. Generally, what we try to do is kind of make it like a little 90-degree angle. For example, I can take the Br, my C, and my I. And I'm going to keep those basically set into the board. What I'm going to have left will be a solid wedge for my hydrogen and a dotted line for my carbon atom. Now, equal what I end up doing, I randomly pick bromine, carbon, iodine. Equally, you could have picked it in which we had bromine, carbon, and hydrogen being set. Br, hydrogen being locked. This carbon atom is still going to be down, and this iodine atom will also be forward. Now, as far as our arrangements, one arrangement is a little better than the other one. In this particular arrangement, what is hydrogen, forward or backwards?
Forward.
In this particular
Oh,
drawing,
it's on the same.
it's in the same plane. On this particular part, now just between this molecule and that molecule, this molecule, there is no solid lines or wedge lines. On here, I've already defined some groups being solid lines or wedge lines. The only groups that have actually been defined as being forward would be the I group and the C3 group. I is forward, C is the group being backwards. The H group in this molecule here is neither forward or backwards. It's locked to the board. So now remember, earlier we can actually assume that because on the side we're basically make it forward. But that's only if you have no groups actually defined as being forward or backwards. If the person wanted to be forward or backward, they're actually going to draw it in either a solid line or a dotted wedge. I mean, a solid wedge or a dotted line. They did draw a solid wedge and dotted line, but they didn't do it for hydrogen. To do it for hydrogen atom, we got to then rotate the molecule. I am not a big rotator of the molecule. Some classes actually rotated more, and some standardized exams also rotated more. But we can show you how to rotate the molecule. And rotating this molecule, for example, rotate the majority of the one will rotate. I got a C, a Br, an H, CH3, and have an I. And I'm going to do as far as what they call an allowed rotation. For an allowed rotation, I'm going to lock my carbon atom in another group as far as being set, as far as not moving it. The easy one as far as lock will be a carbon atom and a bromine atom. I'm going to lock those in place. What I'm going to then do is then rotate the rest of the atoms. Do I want my hydrogen atom to be forward or backwards? You can make either one of the ways. But again, if you don't want to have to change it up, you make it backwards. Then if you put it forward, you got to change the little RH configuration up. So for example, I want my hydrogen atom to be backwards. I am going to lock carbon and bromine in place. And I'm going to rotate the other groups. So I want my hydrogen atom to be here. I'm going to rotate my hydrogen atom 120-degree angle to be here. If hydrogen is rotated here, the carbon atom is going to rotate where I is located at. And I is going to rotate to where hydrogen is located at. So we're going to have dotted line, H, solid wedge will be I, and undefined line would be, the C3. as far as rotating it, in which I will put the hydrogen atom being back. You also can rotate in which the hydrogen atom will be forward by doing the exact opposite rotation. If you do it correctly, both arrangements will give you the exact same RS configuration. Remember, right here I actually rotated to put the hydrogen atom being backwards. I'm going to rotate in which I'm going to put the hydrogen atom being forward.
So the first one is it going backwards, you said?
I rotated the hydrogen atom so I put it in being a backwards position, the dotted line.
Okay.
Equally, let's for example, somebody wanted to leave it in being forward. In which I'm going to do the same molecule. I got C, Br, got my H, solid wedge, I, dotted line, CH3. Again, I'm going to lock my carbon and my bromine bond. And I'm going to rotate the other groups. This time I'm going to rotate my hydrogen atom going to where the I is located. I is going to dip down to where the CH3 group is located. CH3 will go to where the H is located. All you need is rotate out group. When you move one, all the rest are going to move two. So here we're going to have an H being forward. Dotted line will be an I. And you got a solid wedge, a straight line being CH3. Now we do it based upon like a rotation one. We should get the exact same RS arrangement in actually both of those rotations. If we get a different value in those two different molecules, then we end up doing something wrong. We just do the little RS configuration and we'll call it a week. And we got I, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3. Counterclockwise makes it S. We have 1, 2, 3, which is clockwise R. Who get the final say so? Who gets the final say so? 4. 4 is forward. Makes this molecule also be S.
So that was already an S, right?
Both came from the same molecule. Okay. So both of these should give you the exact same answer. What I want to point out, that it didn't really matter which one you actually picked to put it forward or backward. It didn't really make a difference. You still would have got the exact same answer you did if you rotate the molecule correctly. It would give you the exact same answer. If you got two different arrangements and you did something wrong. But that would be a wrap as far as this week goes.